thank you very much for having me. I've never given a talk in a barn before, so much appreciate the chance to do that and to meet with the Berryville Institute of Machine Learning. I'm going to talk about my students and I are doing on understanding what a model might leak about what it's trained on. And privacy is a very loaded word. I want to first talk about privacy in general, that we usually think about privacy as privacy of data. We do a computation on some data, we compute some function on some inputs, and the type of risk that we talk about is the risk of the data that we're computing on being revealed. Okay, so that's data privacy. We have data that is being collected, being stored, being used in computation, and we want to protect it. The other kind of privacy risk is the one that I'm going to focus on in this talk, is inference privacy. That we have some output of a computation that we intentionally reveal, and the concern is that based on that output, it will be possible to infer things about the inputs that might be sensitive. So that's the focus of this talk, is on inference privacy. Both of these are issues in machine learning. The output of computation in machine learning is typically a trained model that we've trained on some sensitive data that was the input. And there's a lot of work to try to do that, protecting the data. So that's the data privacy problem. In some ways, that's a well-defined problem. We know exactly what it means to protect the data that we're computing on. We have well-defined solutions. It's not a completely solved problem, but it's a well-understood problem. And the main issues there are, can we make it cost-effective, and can we provide the right incentives to make businesses want to do things that way? The inference problem is about limiting what can be inferred from the output, and in machine learning, that means limiting what you can infer about the training data, or maybe even the training process, from the model that's released. And that's a much less well-defined problem. That's one where understanding what might be inferred is very different from understanding other kinds of leakage. And so a lot of the work is trying to understand what might be inferable from the model. The biggest tool that exists for this is differential privacy. Differential privacy is a formal model of privacy that allows us to at least talk formally about a very particular kind of leakage. But it's not well understood what that might mean in practice and what actually matters in terms of privacy. We have this formal definition of privacy and a lot of advances in the theory, but a really big gap between theory and practice. I'm going to briefly introduce this formal definition. So it provides this very strong theoretical bound on what any adversary could infer to distinguish between two neighboring data sets. So it's a very precisely defined notion of privacy, but it's also a really limited one. But one of the appealing things that it has is it has a parameter that controls, that allows you to talk about the inference bound. It allows you to talk about how much more an adversary can predict about an inference based on what's been revealed, in the case of machine learning, the model, than what they could without it. But it applies to any kind of computation, any kind of data that might be exposed. And so this privacy parameter allows us to make trade-offs. We can talk about amounts of privacy in terms of this privacy loss budget, and if it is high, that means we can reveal a lot, we don't need to add much noise. The mechanism for providing privacy is almost always adding some kind of noise to the computation. If we add enough noise, we can have very strong privacy guarantees. But we're always trading off the utility of the computation in terms of the amount of noise we need to add to get privacy. And so when differential privacy is used in practice, you've got to set this privacy budget. And how this happens, at least in the best cases, it happens there's some policy committee that's charged with pick the value of the privacy parameters. They might have some notions of what's getting exposed at different levels, but those tend to be pretty uncertain and fuzzy and maybe come from experiments more than come from theory. And they come up with a value of this is the privacy parameter you should use, and then you use an algorithm that's been proven to satisfy differential privacy, but with that fairly arbitrary choice of privacy parameter. An example of this in practice, Apple uses differential privacy to collect data from people's iPhones. One thing they collect is use of emojis. They've got a lot of PR announcing this at big events. But setting the privacy budget for that is quite arbitrary. Right? So they select the privacy budget as epsilon of 4, but 4 per day, keeps resetting. Right? The privacy budget for the typing, which maybe is more sensitive than the emojis, well, that's 8. Right? And these are really set based on not some notion of what the risk of different kinds of inferences might be, but what the smallest privacy loss that produces tolerable utility is. With most machine learning algorithms, at least the kinds of ones we're talking about with deep learning, ones that are doing complex non-convex machine learning, well, these trade-offs look pretty bad. So if you look experimentally at the utility you get as you adjust the privacy loss budget to levels that might provide meaningful privacy, basically the model doesn't learn anything. There's progress in that, there's advances in that, both tightening the interpretation of the bound and training models with privacy that maintains some utility, but it's still a huge way off from being able to have acceptable privacy utility trade-offs. That you could say, well, maybe acceptable privacy loss happens somewhere around epsilon 1 or epsilon 3 if we're kind of aggressive thinking of what that inference bound means. Acceptable accuracy loss for most industrial uses or meaningful uses of machine learning, you're not going to give away more than a few % of accuracy to have privacy for most use cases. So we want to be in that green region on the graph where we actually are is miles away from that. So that's kind of about the state of the art for what we can get in terms of theoretical privacy utility trade-offs. So the real question that my research focuses on that we're talking about today is how much is really leaking? Is what's leaking from these models really enough that we should be concerned and need that level of privacy guarantee that we can get from differential privacy? And it's also the case that, well, that only guarantees one very particular property of distinguishing between neighboring data sets at whatever unit of privacy you define that at. Lots of the privacy issues that we might care about are not covered by that, and I'll introduce what those are soon. But the other thing, like differential privacy as a theoretical result, is making claims about the worst possible attack with no other limits, right? So a realistic attack cannot achieve that worst possible result that differential privacy is guaranteeing. So maybe there's a big gap there. So that's where privacy experiments comes in. We want to understand what the actual inference risks are to a realistic adversary. That includes ones that might be covered by differential privacy, as well as a lot of inference risks that are not, and develop methods to try to empirically measure that leakage risk. The one big worry about any kind of empirical method for considering security and privacy is, well, you're only getting to measure what the current attacks that you can think of today can do. Right? So you have to be very careful to not make assumptions based on that in case attacks might get better. Right? So you have to think about sort of what the space of possible attacks, or at least view your estimates in terms of this is a bound on what we know today. But there is a strong case for looking at privacy through experiments. Right? Partly, the theoretical bounds are usually, we can get a nice theorem, we can prove a property, but it's a long way from being meaningful. It's proving a property where the inference bound is so close to 1, it's not actually meaningful. It also can only address certain risks. So we can test empirically for many risks that we don't have any theories for, ways to quantify that way. And so we can use experiments to meaningfully estimate leakage and understand what these risks might be in practice. So I want to talk about two different kinds of inference risks. Both of them are in the space where the adversary has a model. They're learning something about the data that was used to train that model. The kind that gets the most attention is dataset inference, where they're learning something specific about specific records in that dataset. And that's a meaningful risk. We'll talk about that. The other kind is the one that is not studied as much, but I think is actually a meaningful risk and deserves attention that we'll talk about, is distribution inference. This is a question of, they're not learning about specific records, or at least that's not their goal. Their goal is to learn something statistical about the distribution that the model was trained on. That's a different kind of risk. From the differential privacy notion of privacy, that's not even relevant. Right? Differential privacy doesn't use the statistical properties as not private. But for lots of real-world scenarios, the statistical properties of the data are private. Of course, the goal of machine learning is to build a statistical model of the data it's trained on. Right? That's kind of the whole point of machine learning, is to train a model to capture statistical correlations in the training data. So this raises a pretty interesting question of, well, what's a privacy violation and what's the actual purpose of machine learning? Can we separate those two? So I'll give some examples of both kinds of risks. And we're going to start with what's the most commonly studied risk and probably the simplest one to understand, but the one where the actual privacy implications of it are much less clear, which is membership inference. There's definitely good reasons to study it, right? It's the best defined risk. It can be a serious privacy risk. What membership inference allows the adversary to do is if they know a record that might or might not have been in the training data and they have the model that was trained on a data set, they can predict, sometimes with enough accuracy to be useful, whether that record was in the training data or not. This might be relevant in a medical scenario where you're training a model on patients that had some disease or some property, and you're learning whether a property about the patient by seeing if their record was used to train that model. So in a generic membership inference attack, right, the adversary is starting with some pool of candidates, as well as a model that was revealed to them in some way. And usually we assume they have full access to the model. We could assume less access. They could maybe only have an API access to the model. And most of the attacks still work. And the model that's making a prediction is going to output a prediction of how likely it is that that candidate is a member of the training set. And that's usually a number in some range, and the adversary ends up wanting to make a binary decision, yes or no, was this a member? So they need to select some threshold where if the prediction is above that threshold, that means it is a member. If it's below it, it's not. So turning that threshold into a binary prediction. And the first approach to do this, and one that variations on it are still among the best approaches, is to train meta-classifiers. You train models with different data sets, some that have the record that you want to test and some without, and you see which, and then you train a meta model to distinguish those two, and then you learn something about a model that might reveal whether this record was in the training data or not. A much simpler attack that in many cases also works as well or sometimes better is just to look at the per instance loss. If the model, the intuition is that if the model was trained on a record, it will be overfitting to that record and have higher confidence in that prediction than it would on ones that it wasn't trained on. So the ones that have the lowest per instance loss are most likely to be members. And then you set a threshold. In the case of the YUM attack, they set the threshold based on the expected training loss. And ones with lower than expected training loss were classified to be members. Ones with higher training loss were not. To evaluate and understand the leakage, we have to think about the goal of the attack. So one way to measure that is just to look at advantage, to look at the true positive rate of the predictions versus the false positive rate. And if that is high, that says the predictions are giving you an advantage, you're doing better than random guessing on the membership. The problem, this doesn't really capture a realistic adversary goal. The adversary goal is to, at least in most scenarios we think about, to with some high confidence identify some members. Right? So the average doesn't really matter. What matters is, are there some candidate records that are exposed badly enough that the adversary can make high confidence predictions about them? And we usually view this in an asymmetric way, that predicting membership is a higher risk than predicting non-membership. There definitely are scenarios where predicting non-membership would also be a risk, and there are attacks that are much more effective at predicting non-membership with high confidence than predicting membership. But we're going to assume the asymmetric goal is to predict members with high confidence. The metric that measures that better than the advantage would be to look at the positive predictive value. When the model predicts an input as a member, what does that mean for the likelihood that they actually are a member? One other factor in this is you're starting with some set of candidates, right? If the prior on those is half of those are members and half of those are not, which a lot of the experiments do, random guessing, you're going to be right half the time. You're going to be in a scenario where it's easier to predict membership. Many of the real-world scenarios we might care about, the prior is going to be much lower than that. Right? If everyone's equally likely to be a member, maybe the risks of being identified as a member are pretty low. It's probably not that harmful to be a member if half of the candidate set is members. Right? So that impacts things a lot as well. So what we really want is attacks that provide high confidence of membership even in settings where the candidate pool is mostly non-members. And the problem with existing attacks, there's no threshold that allows you to do that. So you can adjust the threshold to trade off the false positive, false negatives that you get. But you got to pick some threshold if you want to make a binary decision. And for attacks like the per instance loss attack, there's no threshold that will allow you to have a high PPV. If you pick the threshold that maximizes PPV, you're going to get up to about 0.8, which it's hard to imagine scenarios where having 0.8 PPV that someone's a member in a prior setting where you're starting with half, you'd have to be a pretty draconian adversary for that to have some harmful consequences on the individual. So we need attacks that have higher PPV for some inputs, even if they are not identifying as many members as this attack. One thing you can see on this slide is that the privacy noise that's added to guarantee differential privacy, even with a very high privacy loss budget, just a little bit of noise is enough to change the loss function so it smooths out and you can't easily distinguish the members. Those curves start to look the same, except for the non-members now have a very high confidence identify as non-members. So if you care about both sides of that asymmetry, then even the privacy defenses might actually make things worse. The attack that Bhargav came up with, Bhargav is one of my PhD students, to try to get a better trade-off and have the higher PPV on the ones that it identifies, is looking at the loss value still. So it's still a very inexpensive attack compared to ones where you have to train meta-classifiers. But now looking for local minima in the loss curve rather than global minima. So that means all we're going to do is sample points around the input point and see if the loss for those sample points that are nearby is higher or lower than the original loss. If it's higher for most of the points, that suggests we were close to a local minimum, and that was more likely to be a member. Right? And you can still set that threshold for how many points have to have a higher loss to conclude that you are at a local minimum sufficiently strongly to be a member. And this is, the threshold now is what's called the Merlin ratio. And we have an opportunity to distinguish. You can see the blue line for members has more instances where that test says most of the points nearby have a higher loss, so we're near a local minimum loss function. And we have an opportunity to get, for a small number of points, a very high PPV. It's identifying a small fraction of points that are most obviously overfit to by the model because of being at these local minima in the loss curve. We can do even better if we combine that with the global loss. So that places where it makes bad predictions are places where the loss is already so low it's a minimum because it's at loss close to zero, or maybe even ending up at exactly zero, which many of the points do for this model. So that little region where we can have cutoffs for both the global loss and the Merlin ratio ends up with a very high PPV for a very small number, but in terms of the risk, that seems like the risk to individuals or to who those records correspond to, that's much more significant than having a large number where the PPV is 0.8 or some much lower PPV that you can't really get actionable predictions from. Okay, so that's an example of a dataset inference attack where you're learning a specific record in a dataset, and that seems to all result from when you train a model, it's going to overfit to the training data. Okay? Any overfitting might be revealed by the model and reveal something about the training data. The next kind of attack I'm going to talk about is a distribution inference attack. And this is a very different kind of attack. This doesn't depend on overfitting because it's about learning the distribution. Right? So this is definitely within the goals of the model is to learn the distribution. And the question is it learning something about that distribution that should be sensitive and kept private and is not the goal of the task that the model is being trained? So this is a very different kind of attack. Just to give you an example of what it might mean, as a toy example, we have a model here training on a very secret data set that looks an awful lot like MNIST, but let's assume it's a secret MNIST. And it's being trained for the task of predict which digit is the input, the standard MNIST task. And so it's supposed to capture statistical properties of how people write their digits. But it might also capture other things. So an adversary might want to learn, well, what fraction of the training data was written by people that slashed their sevens? Because that's very suspicious when people slash their sevens. I slash my sevens. It might mean they're Canadians or British or something like that. So if you could train a model that would, from this model train to predict digits, which seems like a good public thing, now learn that, say, 15% of the training data had slashed, of the sevens in the training data were slash sevens, well, that might be something you don't expect the model to leak. And this toy scenario is probably not that sensitive, but you can imagine scenarios where it would be sensitive. And there are attacks like this. They're often called property inference. We're calling them distribution inference, which I think is a broader name that includes other things than just some fraction of the data having some property. But the general kind of attack is there's some statistical property of the data in the training data, and that's being leaked by the model. To understand this better, we want to formalize it. And formalizing it is tricky because we have to separate what's the attack distribution inference from what's the model being trained to learn about the distribution as intended. So to start, membership inference has been formalized well as a cryptographic game. Cryptographic games seem to be at least the best way we know to formalize properties like this. And so you're setting up a game where the adversary's goal is to distinguish between two things, and if they can do better than random guessing, then that says that they've learned something that's the leakage for the inference. For membership inference, there are two models, one trained on a data set that includes the member, one trained on a data set that was not. You randomly provide those models to the adversary, one of those two, and the adversary predicts which one they got. If they can do that better than random guessing, something is leaked. So to turn that into a model for distribution inference, well, we don't have that clear scenario where there's one record we're looking for. Right? We're trying to distinguish distributions, and the key to defining it as a problem is to say, well, we can't just take two arbitrary distributions and say, can we distinguish them? We want to look at it from, there's some underlying distribution that's public. And then there's some function that produces a different distribution. So we can have two functions that produce different distributions. One could be the identity, so that would be the underlying distribution, which could be what we know about all people. Right? And then there's some bias in the actual training set that produces the different distribution. And now we train models on those two distributions, so we're still sampling a data set from those distributions. But now we have two well-defined different distributions that we're thinking about, and the adversary's goal is, can they predict which one the model is trained on, a data set sampled from one of those two distributions. And we can measure that, and we can do experiments to infer it. This is an example of if we are training a model on the Celeb data set, which is pictures of celebrities, the task is to tell if they're smiling or not. The inference goal is to tell what fraction of the training data set are women. So what's on the graph is saying the accuracy of predicting between those two hypotheses of was the female proportion of the training data 50% or 0%? Well, 90% of the time we can correctly predict between those two. As the ratios get closer, the predictions get much less accurate. And you can see results there from a strategy that is similar to the meta-classifier strategy for predicting membership inference with some new tweaks to make it work on the models for distribution inference. Okay, so we can do other kinds of properties like if you have a graph predicting the average node degree of the nodes in the graph that was trained. These are both binary classification tasks where we assume there are two candidate hypotheses. Much more realistic to think about an adversary that doesn't start from candidate hypotheses but wants to, as accurately as possible, predict some property. That property is, in this case, we're focusing on ratios. So the alpha is the ratio of some property in the data set, of records that have that property. And to get a better handle on how much is actually leaking, we have this notion of n-leaked, which we can define for different kinds of distribution inference task, which is capturing the notion of if the adversary was able to just sample directly from the training distribution, how many records would they have to sample to make similarly accurate predictions to what we observe from what they can predict from the model? So the nleaked is a way to think about how much is leaking separate from the question of, well, given the distributions are more different, you're going to have a better chance of predicting which one, distinguishing. So for the regression task, so you can see this is an example for RSNA bone age as a data set of images of x-rays of bone hand scans. The model is trained to predict the age. That's the standard task. And then the inference property is what fraction of the training data is female. And you can see the regression predicts quite closely what that fraction is over a large range of possible alpha values with a fairly low mean squared loss. And we can look at that in terms of nleaked, comparing different data sets, different ratios, different properties, and see that this is actually a case where a huge amount is leaked. That the nleaked value for this is over 200 on average. For the Celeb case, it's more like 10. Right? So thinking of, well, if you could sample 10 records from the training distribution, you learn quite a lot about that distribution. For many cases, we're down where it's only a handful, and with the binary test, often less than one. But this is the way to quantify sort of what's really leaking. Right? But leaking 200 records from your data distribution is definitely a lot. Right? That's the notion of what this is measuring. So there's a lot of variance there. There's definitely places where you're leaking a surprising amount of information. Okay, so we've seen examples of both distribution inference and dataset inference. Both of these have been sort of at the level of records. So the next thing I'm going to talk about is at the level of attributes. And we'll look at this both from a dataset perspective and from a distribution perspective. So for both of these attacks, the assumption is that the adversary has partial information about some record that might be in the data set. But there's some sensitive attribute of that record that they don't know. So as an example, from the census data, you might have an adversary that knows the age and the education and all the fields in the record, but doesn't know the sex of the individual in that record. If that's, and in that case, that would be the sensitive attribute. And their goal is to have a prediction algorithm that, given this data that is missing the attribute and the model, to predict the missing attribute with as much confidence and accuracy as they can. This is also an asymmetrical problem, and often it makes sense to think of it as, well, there's one value of that attribute that's sensitive, and if they can predict individuals that have that sensitive attribute with high confidence, that's what the real risk is. So the big question in attribute inference is if it's really because of the model being revealed, or this is just imputation. Right? So a lot of properties that are attributes, if we know something about the data distribution, we can predict them pretty well, whether we have a model or not. Right? So lots of attempts to do attribute inference are making predictions that are much worse than we could already make without the model. So that's maybe not really an attack if that's what's going on. But it's actually pretty interesting and hard to distinguish those two. And then you can think about scenarios, well, the imputation depends on having access to the distribution, which maybe the adversary doesn't have very good access or knowledge of the true distribution and is making predictions based on a less good distribution, so the model will know. So those are the kinds of things that we want to distinguish. Definitely the imputation risk is real, right? It can be harmful when properties are imputed about people, but it's kind of inevitable. If it's based on public data, and training models on public data do imputation, there's not a lot you can do to prevent that. You can maybe have regulations that limit the harm from it, but there's not a lot you can do technically to prevent imputation based on public data. Okay, so how did this look in specific examples? So here's if you train an attack on to do attribute inference to make predictions about the gender based on this is a model trained on the census data, you can predict pretty well. So the standard task with the census data is predicting income. And this the standard data was 1994 census data, and high income was over 50,000, low income was under 50,000, so it's a binary classifier to predict those two. We've done a lot of experience constructing data sets of more recent census data that have larger data sets and be able to play around with different tasks and see how these things vary. But the prediction here is looking like you're doing better on the training records than the testing records, which looks like, well, that's evidence of an attribute inference attack. The model is helping you make better predictions. Still not super highly accurate, so 60% accuracy might not be enough to be actionable, but definitely seems to show that there's some attribute leakage. But if you just do imputation, well, you can do as well. So maybe what's going on here is the model's being trained, is learning something about the distribution, and you're seeing the attribute inference because of what it's learned about the distribution, not because it's leaking something about particular records. So that's what we want to understand and be able to distinguish and understand what the limits of attribute inference are and where the risks are real. So the model of the attack is similar to for membership inference. If it's a black box attack, they have API access to the model, they only consider its output, they have a set of candidate records, and if it's an asymmetric sensitive value inference, let's assume in this case that the sensitive value is being female. Societally, we can argue, and sort of this maybe is not the best example of the sensitive value, but that is what's used in experiments. And the adversary's goal is to identify from the set of candidate records with unknown sex attribute the ones that are most likely to be female. The standard way of doing this is to consider just reduce it to membership inference. Right? You can test the records with both values of attributes, and if your membership inference oracle is good enough to tell you one is more likely to be a member than the other, well, that tells you the attribute. This means you're limited to as good as your membership inference might be. And if you try that in practice, it doesn't do better than random guessing in most cases, and it doesn't seem to be actually working well enough to get the attribute inference, just to show that there's a risk, which might lead you to conclude there's not. So the way to read these graphs, so the scale on the horizontal axis, we're sorting the records by the confidence of these predictions. So and this is a log scale. So you've got 10,000 candidate records. You're trying to predict the ones that are most likely to be female. And if you say just take the first point, that's going to be the first point. How accurate are you in predicting that? If you want to identify 100, you're going to go up to the 10 to the 2 point on that chart. And here, none of them are getting much above 0.5. So you're not predicting anything. Whereas imputation is actually pretty good on this data. So imputation, at least you're above 0.6. And your higher confidence predictions are getting up to about 0.8 on the very high confidence records. Maybe not enough to be a risk, but showing that, the model's not what's leaking it, it's what we know about, from the distribution. To make the attacks better, we're looking at, now you've got access to the model, is there a white box attack, where you can actually take advantage of looking at what's going on when the model performs inference. And the idea for this is to say, well, are there neurons that are activated in ways that reveal something about, are there training records of the sensitive attribute type that would activate those, and can you identify those neurons? So if you look at the neurons in this simple network, you do find that there are ones that seem to be correlated with the attribute that you're looking at. Right? So if you take the 10 neurons that are most correlated with attribute equals female, you see that those activate a little bit differently on records that are true female records from records that were male records with the attribute flipped. So that's what's going to be used to make the white box attack distinguish and predict the attribute. And we can see the red line on this graph is now showing that the white box attribute inference attack. So because it's attribute inference, we don't expect it to do anything on the test set, which is kind of what we see with the dashed red line at the bottom. That's very close to random guessing, other than, well, it kind of does a little bit like imputation. So it's still learning from the model. Whereas the white box attack for a handful of records is making very accurate predictions and putting those at high risk of being identified. It's still a very small fraction of all the records, and it doesn't do much better than imputation, right? It quickly does worse than imputation. By itself, you can combine it with imputation and do better, But the biggest risk, at least if you think of the risk to individuals, is ones where the imputation would not put them at risk of being identified with a sensitive value, but because they provided data to train the model and the model was released, now they're at risk of that. And there are some records like this. So you can see in the scatter plot, there are points where the imputation would have high confidence that they are male, but the model, if they were part of the training data, the white box attack on the model would have high confidence that they're female. Right? So that's the case where the model is putting an individual at high risk. It's a small fraction of records, and one of the big open questions is why are those records vulnerable? How does it vary across the distribution? But there's at least some strong signs that there are reasons we need to think about attributed inference, but we need to think about it carefully in terms of what the models are being that imputation would not. So those are the examples of distribution and dataset inference attacks, right? In the case of attributed inference versus imputation, distinguishing those is a hard challenge, right? Because the model reveals things about the distribution as well as things about its particular data set. I'm going to, before I conclude, talk a little bit outside of this about sort of privacy research in general. And there's a great talk that Alex Stamos gave at Unlearning Security a few years ago that talked about the real state of security. And he has this Stamos hierarchy of actual bad stuff that happens to people online as he was CISO of Facebook and Yahoo and sort of had a lot of visibility in the bad stuff that happened to people, and talked about how the security research community, well, what we work on is that top of that pyramid, and most of the papers in an academic conference like Usenix are in the top pixel, and if you divide the pixel into the red, green, and blue, well, you can find the side channel attacks that are the big focus of a lot of the research papers. And that was for security. For privacy, I think there's a similar pyramid, and I'll take the liberty of renaming it, that a lot of the privacy harm is much less clear than security harm in most cases. But the big privacy harm, the big privacy risk that matters is really the data collection. Right? There's massive data collection, there's massive exploitation of that, some of that might be harmful to people. None of the research is really probably going to help us much with that, because that's intentional collection and intentional use of the data. There are some places where research can help. As academics, we can work on the top of the pyramid, and we probably should, driven by curiosity. And probably the inference privacy things that I've talked about, they're pretty close to the top of the pyramid in terms of, these are things definitely there are risks, and it's important that we understand them. In terms of the risk that most people face because of privacy online, they're probably not inference privacy risks. They're really the data being collected and used as intended. But it's hard to see where, at least as interesting scientific questions that academics can study will fit into that. There's definitely legal, regulatory issues as part of that. The one thing that I think is important for academic researchers in the space to think about is most of the work that's going on in this is being funded by people that are on the big part of the pyramid that is doing the massive data collection and exploitation. Whether that's companies like Google and Facebook, but it's also true of a lot of the government funding that supports privacy research. It's coming from parts of the government that are big on the data collection and exploitation side. So I think, as academics, we definitely want to stay at the top of the pyramid, but make sure that we're doing things that are not overly influenced in the wrong ways by the parts of the pyramid that are focused on the data collection and exploitation. So to close, I want to return to the technical theme of the talk, that we really want to close these gaps between theory and practice. There's a lot of differences in what we can say theoretically about privacy risks and what they actually are in practice. The formal privacy guarantees that we are able to make using differential privacy and variants of that are really the only formal tools that we're able to use usefully now. They're rarely strong enough to provide meaningful privacy guarantees, even though the theory is sound and true. And they can't capture many of the inference risks that actually matter. They're very good at capturing membership inference risk in a certain way, but not so good at capturing distribution inference and the other kinds of inference risks. So there we're left with privacy experiments that can be very useful to understand inference risks, at least understanding where there are cases where it's clear that there are things leaking that shouldn't be, and what kinds of inferences are acceptable. That's really a policy question and a question about the data owners and the data subjects. What kinds of inferences might be used in harmful ways is definitely something that's uncertain. And some of those risks are risks due to imputation, where if the data is out there, there's really nothing you can do about it. But some of those risks are due to models being released, and that's something that we at least can explore and understand technical solutions for. So I will end with that and be happy to take questions.
So I have a question for you. I think the comment you made at the end about trying to tie the theoretical to the actual, let's just say it that way, with the Evans privacy meter or whatever that thing is, the pyramid, is really interesting. And it strikes me that a lot of the work in machine learning privacy is focused mostly on the machine and the data set that's used to train the machine, and not so much work is thinking about the queries that are going to get sent to the machine in operations. How much of what you talked about with regard to, inference distribution is about really the machine, we know about, we can query the machine and pull stuff out about what it's learned in its training set, but we can also learn an awful lot about that we shouldn't know from a privacy perspective just by watching the queries and not even worrying about the machine at all. So is anybody working on that?
Yeah, so there's a lot of, the simplest approach to that is, like, if the queries need to be private, you send the model to the client, and the client makes the queries locally, and you never expose the queries.
Sort of,
but people also want to protect their models.
All
right?
the stuff you talked about, though, with regards to the representations inside of the model could be taken advantage of to lessen the impact of each query or the impact of a particular query by either masking or deleting features that are really not important for the inference being made. So instead, you say, I'm gonna use the model, but I'm not going to tell it everything in this record. I'm just going to tell it the things that it uses to make the real inference I'm interested in.
So that could be in the and we've actually done some experience where the sensitive attribute, you just remove it from the records. Mm-hmm. That doesn't prevent it from being inferred, right? Because it's still, all the things that are correlated with that are still in the data. Even if you've removed it, you didn't train on that sensitive attribute, you sliced it out of the data completely. The actual, and this is sort of the simplest first defense you would try, and we've done experiments with that, it has very little impact on reducing the inference risk or the imputation risk.
Oh, so I got that, but I'm worried about the actually query risk.
Yeah, so the queries, so that actually, there are proposed data privacy solutions to that where you would do a multi-party computation where neither the model, you don't expose the model to the client and you don't expose the query. You're doing it within a cryptographic protocol. For inference, that's still pretty expensive, but it's feasible for simpler models. I think that the setting where you can't send the model to the client and you can't send the query to the model because they're both sensitive and both want to protect their IP or private. Usually the model owner wants to protect their IP. That's why they don't reveal the model. They have a business model that charges for model queries, so they don't want to release the model. Right. Often it's also, for these large language models, they're so big that most people wouldn't want them on their client device. On the cloud right? Couldn't download it. You wouldn't get your query done. Yeah. So that the query is being sent to it, and then if the query itself is sensitive, there are options to do that within a cryptographic protocol, but you've got to then be able to do the inference within that cryptographic protocol, exactly. Which is so far only feasible for pretty small models. Okay. So if you are trying to protect the query and the model, right? They're both owned by different owners. Then there are techniques in cryptography that you can use to do a multi-party computation where you execute the inference as part of the cryptographic protocol and reveal the output to the client with the query, but you don't reveal anything else. That tends to be fairly expensive. There's definitely work going on to try to make it less expensive. And if you trust secure hardware, like SGX, and there's efforts to build secure GPUs and sort of kind of how much you should trust that. You're ultimately trusting the organization making that hardware and key management and lots of things that can go wrong with secure hardware. But then you can scale to the models you can do inference on securely if you trust the hardware that you're running.
So you mentioned privacy budget earlier, and I was just curious a little if you could elaborate on how those values are computed. You mentioned epsilon 1 versus 4.
Yeah, so the privacy loss budget, which is captured by epsilon in differential privacy, is a bound on the ratio of the probability that an adversary, so you've got two things an adversary might be able to distinguish. They're usually considered near neighboring data sets, so it would be the data set with this record added and the data set without it. That's an example that maps to membership inference well. And without seeing the model, there's some probability that the adversary would be able to determine, like their confidence, the probability they would predict that member was in the data set. And then you expose the model, they can do anything they want with it, there's going to be the probability that they now can predict. And what differential privacy gives you is a bound on that ratio. And epsilon, and it's less than or equal to epsilon, that's where the privacy loss budget is defined. And this is all just the definition of differential privacy gives you that inference bound. And so as the privacy parameter says that inference bound is less than epsilon. And then there are mechanisms that have been proven to guarantee that property. And the mechanisms that guarantee that property are adding noise, which scales in some way with epsilon. Right? So if you want that inference bound to be low, and this is why calling it the privacy loss budget makes more sense than the privacy budget, because it's how much privacy you're losing. To make that, so if that ratio is 0, then you're not leaking anything. You can't learn anything. There's nothing that could distinguish those data, then you might as well throw it out. Right? You're never able to learn anything. So it has to be non-zero, and that means you are learning something, but you're bounding what you can learn. And the closer to 0 it is, the more noise you need to add to provide that bound.
So in some sense, though, when you're adding noise, you're screwing your data up.
You are.
So you're screwing your data up on purpose so that some inferences can't be drawn later. And I guess the real trick is to figure out how much can you screw your data up and get some privacy before your data is so screwed up that it's just screwed up data. And I guess when you're doing census stuff, it sort of makes sense because there are some values in census data that have been moved around so much that you get nonsense records. In the aggregate, they work great, but
so
when you go down to like a
is
particular thing, it's pretty silly.
Yeah, and the fact that from a communication with the public standpoint, like the U.S. Census use of it, once it comes out that they're intentionally adding random noise to the data, that's a very hard thing for them to explain. Right?
Try to explain that to a Congress hole.
People who use census data sort of have this, and there's a great article by Dana Boyd about sort of the statistical imaginaries. People are used to thinking of the census data as ground truth. How could you possibly intentionally add error to it for this like silly privacy risk that we did, was not that clear to most people how serious it is, because like the data the census has on people compared to what Facebook has is very little.
Well, I mean,
but there's reasons it's a very real privacy risk, right?
Yeah.
And there's a law, Title 13, that says they have to treat it as a very real privacy risk.
Absolutely.
And so, they have a serious communication challenge as well as a how do you select the right privacy loss budget, and that was really driven by there are use cases that, and the Voting Rights Act is the one that most drove it, that have to have accurate data about the majority and minority populations in districts, and there was some level of error that was the maximum they wanted to see for that is sort of you get the most privacy you can within that requirement. But it's definitely, it's a very unusual, it's a special use case of differential privacy. It's great there's a huge amount of transparency about how they've done it, and sort of how they tried to manage those trade-offs. And in many ways, it's probably the best kind of attempt to do that, but it still has lots of challenges.
Yeah, actually, also, you started talking about the census and how the public responds. I think there was a similar discussion about using sampling in the census. So when you sample, it seems like the descriptions of the practical application of differential privacy to the Apple data is that you end up sampling the activity. So can you describe a little bit more the relationship between sampling and privacy?
So for the census sampling, there's the constitution for the decennial census that's used to allocate the seats in Congress. They are not allowed to use sampling from that because it's, in the U.S. Constitution, they're supposed to count every person. For the data that we're doing experiments on, that's from the what used to be called the American Community Survey. That is sampled, right? They get a sample of the population, they get them to provide a lot of data, and then they understand from the decennial and other methods how to make that reflect the overall population distribution. The privacy risk, sort of, if you are collecting less data, there's less privacy risk, right? So if you can get what you want by sampling from a small group, and they're ones that are willing to be sampled, but maybe you have to worry, is that representative of the full population you're trying to make predictions about? Kind of that raises other statistical questions about sort of, can you do sampling in a way that's going to produce good data? But there's definitely, and federated learning is probably where it's coming up most in machine learning is, you're sampling from a large client population. You can provide privacy on that. If it's large enough, you can even add privacy noise to it and maybe still build a good model of things like what Apple was talking about with predicting the emoji use or understanding how emojis are being used. You don't need data from every iPhone user to understand how emoji use is changing.
So I guess the census data makes a good example because everybody thinks they're in it, or they're supposed to be in it by law.
Everybody's supposed to be in it, yeah.
But as you pointed out rightly, Facebook has a heck of a lot more data on a heck of a lot more people in the rest of the world as well. And I'm interested to know your thoughts about the face recognition data that Facebook collected on billions of people. And then they changed it to face-to-vec representation, and they said, we're great because we deleted the original face data, which struck me as like a meaningless sleight of hand. Is that really a meaningless sleight of hand?
I don't know, I would say it was completely meaningless. It's definitely a deletion of data, and it's sometimes called machine unlearning. Like, you've trained a model on data, and now, and this is true in Virginia, as well as started with the GDPR, someone can issue a deletion request that requires you to delete their data. What that means, I don't think the legal precedents have been set that clearly, but a lot of researchers at least think that means you have to change your model to as though it had not been trained on that data.
Right.
Which, if it's a large, expensive to train model, you can't just retrain from scratch every time someone wants their data deleted. You've got to find some other way to say, how can we remove this data from the model?
So the claim would be, well, we deleted the original data, we just have the face-to-vec data. But that's this.
Right, and you can probably reconstruct the faces from the model, right? So there's lots of research that shows if you've got the model, if it's a face recognition model, you can reconstruct pretty good images of all the faces that it has learned to recognize because they're in the model, right? So deleting the training data, well, I wouldn't say it's completely meaningless because at least there's less risk of the raw data being exposed. It couldn't be used for some other things that it might be useful for. I think Facebook had a patent on sort of scanning the background images to predict how rich someone is from what's behind them in the background and their pictures of people that they're with. That might be harder because the model wasn't trained to, well, maybe the model was trained to do that already, but anything else they think of that they might get from those images, the fact that they've deleted the images at least limits what they might do. But yeah, I would say I'm a little skeptical of Facebook giving up any data that they think is valuable without a big fight.
Well, thanks, Dave. It's a very interesting talk.
Thank you.
Treated me like something that you left behind to stay. Now I'm not sure that I can give a damn.